Okay, so we're going to talk about Dalton's law of partial pressures, and this is going to tie back into the lab that we're doing collecting carbon dioxide, and it also has to do with the air duster lab because both of those labs were collecting the gas by a process called water displacement, or you could say we're collecting it over water. So the idea is this, and of course you want to write these notes down. Pause the video and write what you see on the screen. But the idea is this: if I have a mixture of gases, so let's say I blow up a balloon, and let's say that this balloon contains mostly nitrogen, so these little orange dots represent nitrogen molecules, and let's say these are N2, and they make up about 80% of the gas in the balloon, just like our atmosphere is about 80% nitrogen. And let's say that I've got some oxygen in there too, so it's a mixture. And so let's say I should probably put in a little more nitrogen because we want that oxygen to only be about 20%, right? So Dalton's law of partial pressures basically says the total pressure inside the balloon is equal to the sum of the pressures of the gases that are mixed together in that balloon. So let's say, for example, we had 80% of the gas in the balloon is nitrogen, so let's just keep it simple and say that we have 0.8 atmospheres of pressure due to nitrogen. And then we would have 0.2 atmospheres of pressure due to oxygen. And then together, if I said P total equals the pressure of nitrogen plus the pressure of oxygen, so basically what I'm saying is if nitrogen is 0.8 atmospheres and oxygen is 0.2 atmospheres, the total would be 1 atmosphere of pressure. So the partial pressures are these guys, the nitrogen and the oxygen, which happen to be 0.8 and 0.2 in this case. And they add up to give you your total pressure. So what does that have to do with the gas stoichiometry lab? Well, when you're trying to collect, so let's say this is our beaker with some water in there, and here's our little gas collection tube. Okay, so you're trying to collect 35 milliliters. So this is 35 milliliters of CO2, and we want to know, let's say, how many moles that is. We would say that our moles of CO2 are equal to PV over RT. Okay. Well, here's the problem with that. No matter, even though the gas that I bubbled into this tube from my reaction that was happening, over here in our little flask. So here's where we did our reaction. Little stopper. Here's our piece of tubing. It goes up into the gas collection tube. Oops, didn't work, but you get the idea. Little bubbles go up there, and you get your 35 milliliters of CO2. Well, here's the problem. The 35 milliliters is the volume of the CO2, and the temperature is, whatever it is, room temperature. The pressure, though, is not just due to CO2, because along with CO2 in the gas collection tube, we have a little bit of pressure due to evaporated water, because I'm collecting this gas by water displacement, which means I've got all this water in the tube as well, and some of it is evaporating and creating gas pressure. So what I have to do, if I want to plug the pressure of CO2, so if I want this to truly be the pressure of CO2, I have to take the total pressure and subtract the pressure due to the water vapor in the tube, because there's going to be some evaporated water, and that will actually give me my pressure of CO2, which I would then plug into the ideal gas law. So let's go ahead and just sort of work out how this would work in our experiment. So I'm going to say N of CO2. And by the way, you don't have to change the numbers for your experiment. I'm just showing you how this would work if we were to, factor in the fact that we're collecting this gas by water displacement. So let's say my total pressure, you read it from the computer, let's say it was 100.6 kPa. Okay? Well, that's the total pressure. That's this. What I want to solve for the number of moles of CO2 is I want the pressure just due to the CO2. So I have to subtract the pressure that is due to water vapor. Well, how do I know how much of this is water vapor? I actually have to consult a chart. And you don't have that chart yet, and I'll give you one in class. But it looks like this. Water vapor pressure. And it changes with temperature. So as temperature rises, from 0 to 5 to 10 to 15, you can see that the amount of evaporated water rises, and so the partial pressure due to water vapor is going up and up and up. So let's say in the lab I had a temperature of, 22 degrees Celsius. Well, in kPa that means 2.64 of my total pressure would be due to evaporated water. So what I have to do is, up here, I have to subtract, let me just double check that I have the right number there. Yep, 2.64. I have to subtract 2.64 kPa because that was due to water vapor. And now, once I do that subtraction, this pressure that I have, created now with 100.6 minus 2.64, that is truly my pressure due to carbon dioxide. And then the volume is still 35 milliliters, which is 0.035 liters. The R doesn't change, 8.31 kPa times liters over moles times kelvins. And then my temperature, I think I said 22 degrees Celsius, so that would be 295 kelvins. And now I'm ready to truly solve for my number of moles of CO2. If I don't subtract the amount of evaporated water that from the total pressure, then what I'm really calculating when I get my answer is not number of moles of CO2, it would be number of moles of total gas in the tube. So it makes our answer a little bit less accurate.